Thank you very much, everyone, for joining. Welcome to the first Tech Talk by the Statistical Engineering Special Interest Group at the RSS. So first up, we have our secretary, Alec Erskine, doing a talk on water network burst modeling, history and practice. Alec is a mathematician and asset management consultant who has worked in the civil engineering sector for all of his 40-year career. And originally a hydrologist, he is specialized in the application of statistical and mathematical techniques to engineering and asset management for most of his career. This has included developing the pipe burst models for several UK water companies, which we're going to hear a lot more about. So over to Alec.
Okay, can everybody hear me? Yeah. Okay. Thank you, Roland. As Roland said, I've been working in the water industry for most of my career, or the second half anyway, and I'm more or less retired now. So this talk is about attempting to predict failures in water supply networks, and I've spent a lot of time on this. So this talk feels a little bit like trying to summarize your life's work in 30 minutes. So you'll have to excuse me if it gets a bit rushed. But I'm aiming at about a 35-minute talk. Why do we need? I'll start with what I'm going to break the talk down. I'm going to give you some background, purpose, a little bit of history. I'm going to show you ways of comparing models against each other. If I have time, I'll briefly talk about time series model and wrap it up there. So let's start with the background. The water industry has had quite a lot of quite interesting press in recent years, a lot of it to do with sewers, quite a lot unfairly, but I'll try not to get bogged down into that and stay on what I'm talking about today. Alongside criticism in that sort of area, leakage and bursts has always been an issue with the water company. A surprisingly large amount of water does get lost through leakage, and it's worth just clarifying what I mean by the words burst and leakage actually before I go any further. What we tend to mean in the water industry by leakage is the bursts mean clear pipe failures when usually rung in by a member of the general public, whereas leakage refers to the kind of that, as well as the sort of gentle drip of leaks that happens all the time, often from leaks that are too small to find, and that we do chase down in a proactive way in the industry. So obviously both of these are a bad idea. They waste money, they waste water. They cause the bursts often cause interruptions to supply as well, because it takes time to fix them. And they can even cause serious damage and hazards to health, even some of the bigger ones. Now, it's actually very difficult to measure leakage because we don't really have meters in all the houses in Britain, as I'm sure you all know. We only have meters in about half of them. So it's actually very difficult to even measure it, let alone find it. And the other thing that's always quite surprising is it's very difficult to decide which pipes that we actually should be replacing. Now, a typical water company's got, upwards of 500,000 pipes, and we need to maintain those pipes in some way. So it's actually very difficult to decide which ones are the ones to spend the money on replacing. And at the bottom there, I've just shown you those are the numbers. There is a lot of water disappears in leaks in between us treating it and it getting to your tap in the kitchen, some of which happens on the customer side, admittedly. So I had a quick look at the internet, and there are a couple of these sprung out at me, the ones on screen there. I think finding leakage as I'm sure many people on this call know, is a surprisingly low-tech operation, and it basically involves chaps walking around the streets of our cities with things that look like ear trumpets, listening for leaks. And leaks are still mainly chased on the basis of the sound. I'm maybe exaggerating a little bit. There are more high-tech methods of finding leaks involving, think, correlation of different sounds from different places and so on. But it is surprisingly low tech. On the bursts question of finding pipes that haven't yet started leaking, which is a slightly different problem. It is very difficult, and it has been thought for a while that big data and machine learning techniques will come in and help us with that. You can see there's an article from 6 years ago there that was about using big data, as they called it, to try and help us find the leaks. So I want to talk about building models in order to find these leaks. And you may well ask, what's the primary purpose of these? The way I think of it, there's a strategic purpose and a tactical purpose. And the tactical purpose is all about finding the pipes that are about to burst or are close to bursting, in order that we can replace them. As I said earlier, you've got a lot of pipes to choose from. The thing about clean water pipes is that there's no really efficient inspection technique. It's slightly easier with sewers because there is quite an efficient inspection technique. But with clean water pipes, most of the inspection techniques which have come down from the oil industry are really expensive. And in fact, they're so expensive that by the time you've inspected them, you may as well have just ripped out the pipe and replaced it. And they quite often involve digging a hole. A lot of the best inspection techniques involve digging a hole again, and you've already spent so much money, you may as well replace it by then. So that's really why it's so important for us with our models to try and help water companies decide on strategies for picking pipes to replace. The other objective is a more strategic objective, which is just to help with the finances of a water company and to decide how much pipe to replace, really, how much money to spend this year, next year, the next year, over the next planning cycle. And that's a slightly different problem involving thinking about how fast everything's deteriorating. And so I think it's worth splitting those two objectives, and also mentioning there's a great deal of money involved. In the bottom right corner there, you see I've said there's about £500 million spent on pipes. That's a very rough estimate, but it's that sort of order of magnitude across the industry.
It is.
So burst models. Well, in the early days,
it is
when we inspected pipes, we used a techniques like the Dempsey-Minooq formula, which is basically that formula at the top there, which is all about just saying if we measure the pit depths, in other words, how thick the pipe is now, we know how thick it was when it's installed. We'll assume a linear rate of pipe corrosion, and we'll say, so if it's gone halfway through and it's 10 years old, it's only got another 10 years to go. And that's all that formula's saying. So that was the classic sort of engineering way of attacking the problem. And this is all summarized, by the way, from a quite good report that was released about 15 years ago.
It is.
I think the first paper where people thought about maybe we can do better than that and look at the way the bursts are happening was Shamir and Howard in 1979, which was the first attempt really to do some regression on the actual occurrence of bursts. And things progressed through the 1980s. It was realized that there's a lot of predictors as well as age. It's not just the age that matters. And then a paper in 1982 was the first one to realize that the models were actually so weak in a sense that the history of the individual pipe was really important. And I'll use the word history quite a lot. And what I mean by that is the actual number of bursts that's occurring on that specific pipe. So if a pipe's got, 6 bursts and the next door pipe's got no bursts at all, the one with 6 bursts is a lot more likely to burst. So that's just using the history. Those early models mostly were cohorts. You can see from the dates, they're kind of pre-computing, really. And I think it was realized right in the mid-80s that with better computers coming through, we didn't have to use cohorts. We could do it on every pipe being its own data point. There was also a realization that that length wasn't necessarily proportional, although it nearly is most of the time. And then we get more recently machine learning developments coming through. I've got another slide on a few other sort of papers that I think are quite relevant. There was a realization in the 2000s that essentially we're looking at a Poisson process, or strictly speaking, a non-homogeneous Poisson process, because it's not memory. It is memoryless, but it's changing because the pipe's getting older. Also, of course, there was a big overlap with reliability theory that was also spotted quite early on. And my own contribution is a specific model which is, in my view, quite good at bringing in the history to the regression analysis that you do. And I'm going to speak about that a little bit later, which is loosely called the Bayesian Tuner model and used by quite a few UK water companies. And there's more recent continuing developments. There's a thing called the linear extended Yule process model, which I'm not going to talk about. There's a few softwares as well floating about, all of which use methods that I'm not sure on the detail of. So now these models, what predictors do they actually use? Well, firstly, they use length, which is nearly always assumed to be proportional. The number of bursts you get is proportional to the length of pipe you're looking at. Sometimes it's not quite proportional. We use a little 0.9-ish kind of exponent, but it's roughly proportional, and it's often quite useful to assume it is proportional. The main ones are material, what material it is, what age it is, what diameter it is. Depth turns out to be a bit weaker than you'd expect because most of the pipes are buried at the same depth, because of course they're all pressurized. So you don't need to play about with the depth. You can put them at whatever depth you want. So you tend to put them all at the same depth. Pressure is a big influence, not only pressure itself, but maybe the range of pressure that the pipe's subjected to, and whether it's how quickly pressure is changing. And then we add to that other predictors generated usually through GIS, and I include things like the properties of the soil, the traffic on the road, the amount of vibration that the pipe's getting. Urban density is a good one that is related to the traffic. Connection counts. Every connection is, of course, a weak point in a pipe. Slightly more esoteric things like the climate, the altitude, maybe the distance from the sea. Trees are quite a significant influence on pipe deterioration. The roots just push the pipe about, and you can find a correlation with trees. Although I've got question marks there because I don't think we've ever successfully put it in. But as GIS techniques get stronger, that may well be something that we put in. I should mention the pipe history, which I've already said. When all else fails, you have got this pipe history. How many bursts has the pipe already had in it, perhaps over a window of data. And my comment in bold at the bottom there is that what you have to be aware that a lot of these data sets are not complete in the civil engineering world. So you have to be a bit cautious. You have to use imputation occasionally and be aware that your data is not perfect. So I'm going to give an example here of one of these predictors. This is age, which is always the most interesting in many ways. How are things changing with age? And you can see in that graph on the screen there that at first sight, that looks like, because of the, can you see my cursor? Yes, hopefully. You can see that the slope at the right-hand side of that graph is at a certain angle, and that what we're seeing here is that the burst rate is the up the side, and the year of installation of the pipe along the bottom. So you can see the newest pipes have the least bursts, but as they get older, the burst rate goes up and up and up. Now, is that deterioration? Well, one thing that's noticeable straight away is that it appears to level off before about 1950. So what's going on there? And certainly that's usually attributed to a couple of effects. One is censorship. By censorship, I mean that a lot of these early pipes, we're no longer looking at the full pipe set. We're looking at a subset of the pipes because we've actually ripped quite a few of them out of the ground now, a certain proportion. So that, and we'll usually rip the worst proportion out of the ground. So we're actually shifting the averages by censoring physical censorship there. And the other thing, which is perhaps more obvious, is that certainly in the Victorian era, they over-designed. Pipes were built very, very big, very strong. They were built to last, and they have lasted. So these early Victorian pipes doing very well. However, there is a big complication here, which I'm going to illustrate now with another graph, which is the same graph, but now with the materials split up. And this is very interesting because it kind of shows you that this nice 45-degree shape at the beginning is not what's going on at all, really. What's actually happening is that we are changing from material to material. And so in the recent eras, this is PE, polyethylene pipes, plastic. You can see the steel is low there. You can see the cast irons are all here, and the green is the ductile iron there. And you can see that, what's the one I've missed? Asbestos cement there. You can see that in each color group, the slope, which we're looking for from top left to bottom right, is not nearly as strong and clear a signal as it was when we amalgamated. So this is a false picture of how good the deterioration is and how strongly pipes are deteriorating. This picture here on the right shows that a lot of it is because it's all being confounded by the material types. And one other thing I should mention is that the whole thing is slightly complicated by the fact that it's not a kind of continuously churning system. There's also this effect that we are actually changing from a cast iron set to a PE set, certainly with the smaller pipes. The smaller pipes being put in the ground nowadays are all plastic and have been since since about 1970-ish. Some of the bigger pipes that going in are ductile iron, but essentially we are slowly moving across from a cast iron set to a PE set in the ground. Now the PE pipes so far, and I'm looking at these dark blue dots in the right-hand corner, are doing okay. There's no clear sign of deterioration amongst the older ones. Some of the PVCs are have turned out to be a little bit ropey, some of the early PVCs, but the PEs, the polyethylene, HDPE, I should say, high density polyethylene pipes, which is the vast majority of our pipes going in the ground are now, is doing okay. So to just go back to the main groupings of types of model that are common at the moment, we've got the three main groups, and I would say that snapshot methods is the first group. And what I mean by snapshot method is when you take a 5-year period, for example, and you got loads and loads of pipes, and you calculate the rate of failure for each pipe and put it against the age of that pipe in the snapshot period. So it's a kind of a simple regression approach that treats, say, the last 5 years as a snapshot of as if it was 2.5 years ago, perhaps. And we just model on that basis. And that, of course, can get slightly confused by what is called vintage effects. And by vintage effects, I mean, for example, if the immediately post-war pipes in 1945 had low quality cast iron and they were rushed and they weren't installed very well, and they appeared to be failing at a rate 10% higher than the pipes 10 years later, you shouldn't really say that that represents a 1% deterioration per year, because it's a different set of pipes. The pipes in 1945 are different from the pipes in 1955 because they were probably installed to a different with different types of cast iron that we can't always see in the data, and to different standards. So you do occasionally get these vintage effects that confuse the issue and might exaggerate or underplay the deterioration we're getting. However, having said that, those models seem to work pretty well at pipe picking. To move across to longitudinal effects, we're talking generally proportional hazards models or variations on it there. And now we're not treating the data as a snapshot. We're treating every pipe as a patient, if you like. There's a lot of medical analogies with this, we're using every date of every burst, so we should be getting more data. There's a couple of slight problems that one has to address here. One is that these are recurrent failures. They're not end-of-life failures. So you have to make adjustments to the classical Cox model to deal with that. And the second point I want to make is that we haven't got all the old failures. Our failure data mostly starts in the 80s, and it kind of gets more and more complete as time goes by. So the early data is missing a lot of failures. So you need to be a bit careful of the truncation on the pipes that were around before the 1980s. I'm thinking now that that's probably being less of a problem than I originally thought now. So I think it's having less of a problem because we're not that interested in the performance of a cast iron pipe in its first 10 or 20 years of life, because there aren't any cast irons going in anymore. And the newer materials, we've mostly got most of their failures. So I kind of feel that is less of a problem than I first thought. And then time series methods. This is a completely different idea. What I'm talking about here is just aggregating all the bursts and looking at it against time, and then trying to see the signal through the complications imposed by the weather. So the weather has quite a strong impact on the aggregate burst rate. But if we can take out the weather and build a model without the burst, without the weather, we can maybe see that deterioration rate, that all-important deterioration rate that's so important for our strategic studies. So I'll just explain. I did this talk at the RSS, and I had to miss out these slides because of time. So I've got slightly more time. So I'm gonna do this briefly. The Bayesian Tuner model is it assumes the data as a 5-year snapshot. It's based on a negative binomial regression, and the reason the negative binomial works quite nicely is it is essentially the sum of a load of Poisson distributions, which themselves, their own lambda parameter is itself distributed according to a gamma distribution. So it's quite a flexible way of attacking a Poisson type problem. But the Bayesian tuner arises because the algebra simplifies quite nicely with a negative binomial, such that the Bayesian adjustment that you make to turn a prior into a posterior, in this formula here, the prior is the model rate, and the rate tuning being the word I'm using to mean adjusting the rate according to the history of the individual pipe. The tuned rate follows that simple formula. And it's a bit like the formula that you get straight out of the Bayesian equation, really, where the P here appears both there and on the underside of the fraction there. So you can see the rate model appears in the same way. So I quite like that analogy between the classic Bayesian formula and the formula that comes out of this work. And it's got this parameter A, which is a kind of adjuster that shifts the balance between the model and the history of the pipe. If the model's absolutely rubbish, there's a lot of weight on the history of the pipe. If the model's really, really good, then you put less weight on the history of the pipe. And the size of that parameter comes out of the actual data. So it's determined by the data. So we apply this tuner. When we're applying the model, we apply the regression formula, and then we adjust it with this tuner. That's the way it works, and it has a sort of a net zero effect in the sense that all the pipes with no bursts get their rate pushed down a little bit compared to a pipe with no information. That is, and that makes a lot of sense, because if the pipes had 5 years of problem-free operation, that's a good thing. Whereas if a pipe's had a few bursts, then the rate goes right up. So that's how the tuner model works, and it's fairly successful. The proportional hazards model is of course, I'm sure people on this call will probably be familiar with Professor Cox, who invented it, and I feel I'm teaching people to suck eggs here, but the key point about it is it splits the regression part from the equation involving the time deterioration, as shown in that top equation here. You do need to tweak it a little bit to make it work on the fact that we're getting several failures on a pipe. It's not just a simple end-of-life model, and that's the one thing you have to be a bit careful of. And there are various there's choices there about which way you do it. And we ended up using a total time formulation with a multiplier for recurrence. We found was the best one. But the proportional hazards model uses all the data, and it's not going to get confused by vintage so much, because it's not comparing pipes of different ages if they were exactly the same. Not so much. It could get confused a bit, I think. And it's got this slight left truncation problem, but it's the main alternative. So I want to just talk for 5 minutes about how to assess models against each other. And what we've got here is firstly, we build a model using all the usual kind of regression type ways of assessing models, the BIC, AIC, all that sort of stuff, R-squared. Then what we would like to do is a blind test assessment, well, or at least using data that was not used in the model build. This is all classic machine learning kind of training and testing theory. So, and what it is in effect is a binary classifier. So you're in all that territory of confusion matrices, specificity and sensitivity, precision and recall, ROC curves, all that stuff, which is quite confusing. And as a small word of warning, the accuracy is quite a dangerous one to use because it's well, the main problem is that the trivial model quite often beats the model you're doing, and that's no use to anyone. So accuracy, when you see that, it's not much help in assessing a model. So this is a kind of variation on what's called an ROC curve. And what we're doing here is plotting the proportion of pipe. We're ranking the pipe in order, firstly. So we've got the ones that are most likely to burst at the start, and we're going through them, counting on our blind data set, perhaps a year of data after we didn't use. On our blind data set, what proportion of the bursts in our blind data set we got or were in those pipes. So, for example, this point represents the top 20% of pipes according to the proportional hazards model. What proportion of the burst did they get? And they got 90% here of the burst. So you're obviously looking for a big bend up to the top left-hand corner there, in the same way as a ROC curve. It's not the same as a ROC curve. It's slightly different, and it's using length as well. So there's complications. But a classic ROC curve doesn't work too well for that reason. Okay. Now, the second point is we're actually not interested in most of this ROC curve. The bit we're interested in is down here at the bottom left, isn't it? Because what we're actually going to do with this model is we're going to look at the very worst pipes and we're going to do something about that. We want to know how many bursts we might have avoided. So we're going to look at this bottom left-hand corner, and what I kind of recommend is that if you're going to quote one number about how good these models are, it would be the effectivity at 1%. And what I mean by that is, if we took the worst 1% of pipes, how many bursts of the bursts in the blind test would we have got if we'd magically replaced those with magic pipes that never burst? Would we have got 1% if it was a random model? Probably got 1%. Will we get 2%? Will we get 100%? Will we get 10%? So that's the question. And that's what I'm suggesting is defined as effectivity. And the reason I've picked 1% is it's a bit arbitrary, obviously. The main reason is it's very easy to remember, 1%. But the other reason is it's around about the amount of pipe we might be thinking of replacing in the next 5 years. And that is a planning cycle in the water industry. So it's not a bad number to pick, to look at 1%. So I'm going to show you some results of doing this variation on the ROC curve. Here's 5 different strategies at the top here and how they worked on a water company. And you can see the strategies. You can see that blue line at the top is the proportional hazards model. Remember, we're looking for a curve up to the top left-hand corner. You can see that the Bayesian Tuner model's second most of the time. You can see a random forest model that we've had to go out with machine learning techniques. You can see that the age model is not very good. And you can see that the history model is quite good at the start here, but not very good later on. Now, as I said, what we really want to know is what's going on in this little close-up area in the bottom left. So the next slide shows you that close-up area in the bottom left. You can see that's the same data, but only going up to the 5%. So we're just looking at the bottom left-hand corner. And the effectivity I'm suggesting is quoted at 1% there. But you can see in this area, the proportional hazards is now doing pretty well, really, compared to the others. Second place is a bit of a dead heat between the random forest and the Bayesian Tuner. And then the history model's not too bad. The negative binomial without a Bayesian Tuner is a bit worse. And then if you use an age model, you're not going to do very well. So companies that replace pipes purely on the basis of their age are replacing the wrong pipes, really, if they're wanting to keep their burst rate down. So, okay, just a couple of minutes on snapshot models. I think we're trying to avoid the vintage effect here, and I'll just miss out those two slides. These are the sorts of things that we're looking at for these models. We're looking at taking out purely a time series model, but taking out temperature, perhaps temperature squared. And the reason it's temperature squared is pipes burst a lot more often when it's cold, but they also burst more often when it's hot. So you've got a kind of parabola thing going on. So you need temperature squared in there. Soil moisture deficits, SMD, potential evaporation, days air frost. There's a bit of a reporting problem, which is why the weekends and the bank holidays are in there. And if you take out all these and you're a bit careful about keeping the same set of core pipes through the whole data set, we've now got, you know, upwards of 10 years of data, maybe 15 or 20 in some models. And, you know, you do end up being able to pull out a deterioration rate that is quite useful to us. There's a fair bit of uncertainty on it, I should add, but it's usually in that vicinity of about 0.5% to 1.5%. And that's a really useful number because it allows us to think about budgets. So I'm going to wrap up now, really, with a few comments. I think in this whole topic area, we do have to be careful of the data sets. They're quite weak in some ways, and the further you go back, the weaker they are quite often. And that's in many ways what drove us originally towards these snapshot models that only look at the last 5 years of data. You know, the data that's 10 years old, 20 years old, 30 years old, 40 years old is getting weaker and weaker. So models that need all the data, you know, have got that intrinsic disadvantage of the truncation. Having said that, the proportional hazards model, I think, is coming out best most of the time. The Bayesian Tuner model is not bad. And I've explained to you a little bit why I think effectivity or some variation on it is a really good way to compare one model with another. You may ask what's actually happening out in the real world. And a lot of these models are being used strategically, but they haven't really caught on tactically yet as much as I think they probably should do. So out in the field, what's generally happening is the ops departments go on a history strategy. They tend to replace the pipes that are bursting most. They'll often have a sort of an approach whereby any pipe that's had 3 bursts in the last 5 years, you know, they get in there and they replace it. And that is not the worst strategy in the world. That is a really good strategy, actually. I mean, I think these models will be better, but it's not a bad strategy. I do think it's very important to use history in any model that's used in anger as a pipe picking model. Deterioration works out at about 1% a year. The effectivities that we're actually getting from these models tend to be around, I've written 6 to 8 there. You can kind of see that if the deterioration is happening at 1% a year, and you can get an effectivity of 6 to 8, let's say you get 4, you only need to replace 0.25% of the assets to counteract that deterioration's year-on-year deterioration. Do you see that? So that's that's assuming the pipes we're replacing are magic pipes that never fail, and there's a few, you know, simplifications in that. But it maybe highlights why that deterioration rate is quite important, and the effectivity is quite important. It's the kind of interaction between those two that actually determine how much money we need in the future. As it happens, 0.25% is pretty much what we're doing at the moment. And burst rates certainly aren't shooting through the roof anyway at the moment. They're kind of year on year, they seem to be holding steady. So that's kind of what's happening. I think I'd like to say in conclusion, really, that this whole problem is quite difficult. It's really hard to predict models because you may be saying, why can't you get 100% of the bursts in your top, couple of percent? And the answer is it's really difficult. The models just aren't good enough, even with history. But maybe the next generation of statisticians, maybe the people listening to this call, will be able to improve on these models. Machine learning and AI are obviously coming around the corner very fast. As they always say, it's not always the model that's important, the model form that's important. It's the predictive variables, and there may well be ones that we're not using to the maximum at the moment. And ones that occur to me are we're not actually using the leakage data at the moment. That's top of my list, probably. Leakage data should be in these models, by which I mean when the guys work out leakage for an overall valved off area, that is a number that exists and can be measured. Satellite imagery is probably bringing new things. There may be geographical smoothing techniques as well, so that it's not just the history of this pipe that's important, it's the history of the neighboring pipes as well. I wonder whether effectivities might be a little bit optimistic, in the sense that if we did go out and replace all those worst hitters, then maybe we take the low-hanging fruit. Maybe the effectivity gets eroded. I think the changeover to PE is important. It's not changing very fast. Obviously, at 0.25% per year, nothing's changing very fast. And a better inspection technique would be a bit of a game changer in many ways, because we wouldn't have to go straight to replacement. We could use the model to decide which ones to inspect and then go to replacement, and that would make the model much less important. And that's more or less the situation with sewers at the moment. The other big one really is that the water industry in the UK is under a lot of pressure at the moment, and to the effect that the Labour government may even disband the regulator, which is called Ofwat. So Ofwat really has been responsible for keeping these replacement rates as low as they are. I mean, I think they're too low. I think they need to be a bit higher, personally. But Ofwat has kept them down to these numbers. And if a new Ofwat appears, nobody really knows whether it's going to put more money into research, put more money into pipe replacement, put all the money into sewers, which seems quite likely at the moment, or what. So let's just say uncertain times, really, with the government thinking about these things. And on that bombshell, I'll end the talk, I think. So, any questions?
Well, firstly, thank you very much, Alec. It was a really interesting talk, and certainly a learning experience for me. You can either put your hands up or put questions in the chat. So we have one from Blaze in the chat. Are these models all single level models, or are they multi-level within material, or other high-level variables?
We've tried that. We've tried a few experiments on that question, actually. So I think I've probably tried all the possible things you can do, really. I think that the ones that I've usually ended up with are actually completely separate models for each material. I think the materials are really quite different from one another, to the extent that there are certainly, for a lot of the predictors, you can't go straight across. That, for example, iron pipes aggressive acidic soils will have an effect on them. They'll have a much less effect on plastic pipes. So, there are things that don't go across. There are things that do go across. I've generally ended up with separate models for each material.
Okay. If I could just add a quick rider on that. I noticed you've got things like uh, quadratics and things. Have you tried spline functions where you've got nonlinear relationships between numeric variables?
No, Blaze, I haven't really. I tell you what, because these models are so sort of I don't know if weak's quite the right word, but there's a lot of scatter on them, and I've generally felt that I haven't got, except for the one exception I gave, I haven't got enough signal to be able to say anything other than a straight line. So we haven't really tried that. The one exception that I mentioned in the talk was for time series models only, because you don't need temperature. Temperature doesn't really help with a non-time based model. But the time series model, we get much more failures in the winter because it's cold, and we get slightly more failures in the summer because it's hot. So it makes sense to put a nice little parabolic on there. But on the models that are sort of not trying to do the weather, which are the main models, the Bayesian Tuner and so on, there's nothing that isn't. There was no. I didn't even get any squares in, let alone splining.
Okay.
I don't think. But things may tighten up with better data sets. You never know.
Perfect. Thank you both. Alexandra, apologies if I pronounced that wrong. Oh, I don't think we can hear you. You don't appear on mute. Sorry, no. Would it be possible to type your question? Is that possible? Sorry, nothing. Feel free to type your question. Otherwise, for now, we'll just move on to Lindsay.
Hello. Oh, hello. Thanks, Alec. That was really interesting. In terms of the strategy that they're currently using, and when they dig up the pipes, do they ever do an assessment of the condition of those pipes? Because it feels like that could be useful somewhere along the line.
Yes. Well, the answer is we've not really got that data set into any of the models that I've been involved with, Lindsay, and I completely agree. That would be really useful. Yes. They don't do it enough. I think they do it to a certain level in the field, but the data is always quite hard to track down.
Okay, thank you.
I can see there's one or two people from water companies in the room that might actually know the answers to these better than me. Irving,
Ellen?
for example.
Hi. Yes. Yes. Very nice talk, Alec. Interesting. And I see you work with Tony O'Hagan from Sheffield. So that was because I was going to say, did you know about their work on the stuff? But you obviously did, because you're actually involved in it yourself.
Well, he's a joint author, Eleanor, on that paper that I quoted.
I looked it up while you were speaking, so I did know that. Yes. I was interested in whether you would get different ideas if you took the modelling all the way through to the actual cost of the remedial actions and things that might make it, I was thinking that might make it much more of a focus on the volume of water that might be lost in a typical burst. I mean, presumably they're not all the same, and it depends on the type of, well, the type of pipe and what sort of area it's serving. And I wondered if there were, things like if you were able to look at things like if we see, more than X number of predicted bursts in a sort of certain geographical area, we have a whole blitz and rip out preemptively, more things, that sort of thing, so that it was not a simple strategy of picking a single pipe just because it looks most likely individually to burst, but actually in terms of looking downstream a bit more and seeing what the actual cost would be to, and then optimizing over the cost rather optimizing over most risky pipes, and then feeding that as a sort of fixed thing into a separate model for optimizing cost.
Very much so, I think, Eleanor. I mean, I would expect you to combine this with a cost model. So obviously, some pipes are a lot more expensive to replace than other pipes, size being a clear indication, but the less obvious one is whether they're in the middle of cities or not. So, one's in the middle of cities, you're cost, because of the traffic problems of actually getting at them, cost a packet to replace. So nobody likes replacing them very much. And that's, that ultimately leads us to big problems because our city centre pipes get worse because nobody can face trying to replace them. So, we do have to be careful of that. And I would like to see it brought together with a kind of cost model. And, you could rig up you have to make these things not too complicated, I always think, but you could rig up an easy prioritizer that just took the burst rate and divided it by the cost model. Well, another thing we've experimented with, Eleanor, quite interestingly, is trying to think about how big an effect the burst would actually have.
Yeah.
Sort of in classical risk terms, a consequence to go with the probability. And of course, a little pipe in a quiet little housing estate with a couple of valves at either end is not too much of a problem for us. But imagine if a pipe goes that's a single line supplying a whole village or town. That would be an absolute disaster. So you can bring consequence in as well as cost. So in a way you need three models to do it. Yes, so yes, you have to. There is a sort of secondary stage. And finally, you did mention, did you group pipes into groups? Yes, you would. I think that's definitely the thing to do. There's a third kind of process, which we sometimes call rationalization, which is where you might take the output of these models and then convert it into clumps of pipes that actually form practicable real jobs, and then package them up and then go out to the contractors and get them done. So there's definitely a lot of complexity that I've completely missed out.
Thank you. Alexandra, I know you had your hand up, so we'll try again.
Oh, is this any better?
Perfect, thank you. Go ahead.
Thank you. I'm very glad I've joined this group. The consortium I've worked in before, research consortium, has worked on a very, very similar problem, but with transport infrastructure. So we've worked on the stability of long linear assets, but rail slopes. And what you've shown to date is very similar to the kind of problem that we have, which is you've got your assets, their stability and deterioration is affected by age, by the soil type, by their geometry, by things like that. So I was the statistician in the project, and I used Gaussian process emulation, where you can you basically just use a conditioned Gaussian process on the data. You throw in all of the explanatory variables you're interested in, and it spits out usually spits out a reasonable result with some uncertainty, and it's all done in a Bayesian manner. So you've got, your MCMC estimates, whatnot. Have you considered those kind of methods at all?
I haven't. No, I think there may have been some work that's done in that area, but no, I haven't tried anything yet.
No, the Gaussian processes are quite simple to use, so they won't be too much of a hassle to implement if it improves the predictions. If it doesn't improve the predictions, there's no point using them above the simpler models, for sure.
Yeah, I mean, I absolutely support sort of throwing all these things at the problem in a way, and the middle bit of my talk was about trying to come up with a really good way to compare model against model with this effectivity concept.
Yes.
But yes, I mean, these things need to be tried, really.
Thank you.
Okay, we've got a few more minutes. I think we had a couple of questions in the chat, if I got the timing correct. So one from Alistair, do the burst models have any predictive power for leakage? And then I think a follow-up question from Lindsay, what's the barriers to accessing this data?
Well, I'll just maybe mention what leakage data is like. Firstly, it's to measure leakage. It is again an area that probably us statisticians should could help a lot with, I think, because it's a bit of a black art, and the problem is that you have to guess quite a lot of stuff. You have to make estimates for things. What you do is you isolate a zone with valves on a permanent basis, and then you look at the night flows. But in the middle of the night, you then have to estimate how much people are consuming in the middle of the night. So you can already see there's parameters having to be estimated there. So it is quite a difficult. There is a lot of uncertainty associated with leakage. Having said all that, I do think it would be a predictor, and it is, of course, a bit blunt because you don't get it on a pipe-by-pipe basis, you get it on an aerial basis. But having said all that, I think it's a slight omission that we haven't accessed that data yet, and it could be done. I think you're quite right, Lindsay. It could and should be done. You've got to try these things. It may improve the model, it may not, but I think it should. They do jump about quite a lot as well, leakages, when they come back from the field, sort of week to week. So it's a little, it's tricky. Do the burst models have any predictive power for leakage? Well, I'm sure they do. That's not something I've tested too much. It's quite funny how separate the world of bursts and leakage actually is inside a water company, and they're not always the same people. So we haven't really tried that. Again, you've got the complication that leakage can jump about quite a lot week to week. So a DMA can be the worst one in the whole company one week, and then it can be quite a lot better the next week. And the smaller the DMA is, the more it jumps about because of the law of large numbers. And they often get negative leakages and unrealistically high leakages in individual DMAs. So it is a bit leakage is an area where statistics could help out a lot. I think with our understanding of uncertainty.
Right, we'll try and squeeze one, maybe two more questions in. So Joy, I think you've got your hand up next.
Yeah, it wasn't really a question. It was more of a just an experience from Northumbrian Water. So it was really a comment on Eleanor's question about how we use our burst models and what we consider. So yes, it's very much like what Alex said. We have a deterioration model, we optimize it, and then we give that information to somebody who creates groups of pipes that can be replaced in a reasonable way. You wouldn't replace one pipe on its own, you would always do them in a geographical area. And we have lots of different tools that help us do that. And then the other question from Lindsay, she was talking about using burst models to help identify leakage. And we are exploring that, because you would think where the risk is highest for a pipe to burst, then you would think that would relate to where leakage may be apparent. So we are working with our leakage teams to say, well, look at these pipes first when you're looking for leakage.
Joy, I'm really impressed that you actually made that big step that in many of my client companies was never made, of using the models, not just strategically, but tactically. And that's really good to hear.
Perfect, thank you. I do believe we've hit the top of the hour, which was the proposed end of it. Unfortunately, I'm sure some people do have to finish there. However, if attendees are available, please carry on. Just while I'm still on the call, I'd just like to flag the SIG has both a newsletter and a LinkedIn group. So if you're interested in further activities of the special interest group and future tech talks, please look out for those. We are planning a second tech talk at the moment. We're currently thinking perhaps Monday, the 8th of December, but we'll be announcing those via the newsletter and the LinkedIn group. And we're also planning our annual AGM, which will happen in the near future as well. So please look out for that. I think Eleanor, you've got your hand up for one final question, but otherwise, thank you all for attending.
Well, I've already had one go. Would you like to pass it instead?
Hervé, is it? Apologies if we're getting that pronounced that wrong.
Yes, that's right. It's not so much a question, it's just an answer to the question regarding condition assessments. So we have tried to link condition assessments, especially condition assessments that were carried out 15, 20 years ago on pipes when we were replacing cast iron mains for issues with water quality. And some of those mains which were deemed good enough were just relined. So we had the information about the corrosion back then. And now we can see that there is a correlation between the condition that they, or the corrosion rates that we were measuring them using the Dempsey-Manock formula and the higher burst rate that we're experiencing today. At the moment, we're not able to completely link that to our burst models because we don't have enough condition assessments. And we do have a big censorship because those bad pipes were replaced when we inspected them. We didn't leave them in. So condition assessment is quite tricky because as Alec pointed, it's quite expensive, so it's quite rare.
Thank you, Hervé. Very interesting.
Right, Eleanor, last question.
Go on. Well, again, it wasn't really a question. I was interested in how all this interfaces with things like BIM, you know, the resource tracking sort of stuff, and new standards on predictive maintenance and all that sort of stuff. I mean, I understand quite a lot of the problem with things like old assets like this is that we just don't have any records about actually where they are, what they're doing, what was in there. You know, we don't know if something is a cast iron pipe unless we dig it up and look at it, for instance. I mean, certainly I know the ones at our house, when they came to mend the leak, they had to find where the pipes went, you know, and it involved digging up rather more than was expected.
But it's a bit harsh, Eleanor. I mean, I've said the data's weak, but I mean, typically you know what the material is for the high 90s% in your million pipes in a water company. Sewers are quite a lot harder actually because it's a lot lower on sewers, but on water pipes the state of the data is quite good. It's more actually the time data that's the problem, that you know the burst data is quite often a bit weak, but the GIS on the actual pipes it's not too bad nowadays.
Okay. And have you been involved in sort of advising on modern standards about what records should be kept with when new things are installed and everything? I mean, is this problem going to sort of go away because we're going to know lots more things and have more in-pipe monitoring or whatever with modern systems? Or
well, I'm not sure it will go away because, as I've said, I don't think there's a really good cheap inspection technique yet for clean pipes. Hervé may have a view on that, and I think I think we go on.
I was just wondering whether, you know, when you buried a new pipe, did it not just have a little cheap sensor with a battery that lasted 20 years sitting on the outside? Yeah. Thing, you know, that sort of thing.
I do think we could do a little bit better on recording exactly what, particularly for plastics, which is obviously the future of the system. A little bit more detail on exactly what plastic has gone in, because there are variations within plastics, and I've not really put that in any of the models as yet. So that it may be that certain plastics do better than other plastics, but the trouble with plastic is it tends to be the joints that are the problem anyway. So it's all about the quality of the joint work that was done by the crew that was out on that day, rather than the plastic matrix. So, you know, there's such a lot going on with these problems, Eleanor. But Hervé may have an addition to that. Hervé?
Yeah, just you know, there's been those talks about, you know, smart pipes and research trying to stick sensors in pipe when they are new and detecting things. It's always difficult and expensive, and you need to maintain those things. Pipes have very long life, and also our renewal rate is very small. So anything that you can do is not going to make any difference. You do, however, have progress in inspection techniques, but they are not able to pinpoint defects. So you have acoustic techniques that claim that they can sort of test metallic pipes on large-ish length of pipes. But you also have on say trunk mains, so mains that are quite large diameter and critical, where you can have acoustic devices put there on a permanent basis to detect, especially on precast concrete, to detect when the reinforced pipes, the reinforced metal are pinging. You know, those wire would break with corrosion. And when you see an increase of those pinging, then you can sort of start to intervene. So you do have techniques, but it's quite niche and specific. We have a lot of, well, literally legacy material and all that stuff. And it's always very tricky to specify exactly the information and the data you need to record when things are put in the ground. It's still a constant tension between what the scientists and the data analyst wants to capture and, you know, the time and effort that this requires, and having that sort of constant, what you are gathering today shall be useful for the analyst in 10, 20 years time. So it's always tricky.
That stuff works for oil, Eleanor, but when the stuff we're pumping around the system costs a penny for a cubic meter, it's a whole different kind of cost framework.
I can see that, yes.
Yes. Thank you.
But and one other thing, the replacement rates we're talking about, which I think I've said are about 0.2, 0.25, 0.3 across the industry %. You can sort of see, Eleanor, that just inverting that implies, if you were to do that in a very, very long term, that implies a lifetime of 500 years. So, you know, that is the sort of lives that some of these pipes may well be living for, particularly the plastics, which, as I've said, they've not been in that long, but they're not showing much signs of deterioration yet. So that's all quite hopeful. And you know, we don't know what they'll deteriorate with really, because they don't corrode in the same way as metal does. But one kind of feels eventually they'll fall apart, but we don't know when.
Yeah. Thank you very much.
Perfect. Well, thank you all. I think that's all of the questions. So once again, one final time, thank you to Alec, and thank you everyone for joining and asking questions as well. I believe Lindsay has shared some links in the chat, but otherwise have a good rest of your day, and hopefully we'll see you at the next Tech Talk. Thank you all.